Hello everyone. Today we are going to talk about a work on VM placement policy on chiplet architecture, specifically some kind of chiplet architecture. And this is going to be our agenda today. And I'll start with, let's get started. So I'll start with the first thing. So it was where it all started. So we were testing few machines. So we were testing few machines. Audible there. Okay. So yeah, I'll start with the thing where it all started. We are doing some regression testing on our new AMD Gen 1 machines that have just arrived, and something that we observed was that when running a hyper workload, basically on two VMs inside the same host, we are seeing a much lower throughput as compared to its Intel counterpart. So if you can see here that the throughput that we are getting here is less than two times of what we get on Intel. So by the way, this was also this used the VertIO NIC. It was using a VertIO NIC, and something that we the first resort that we thought was let's resort to pinning within a same NUMA node, and that is where we observed that based on the pinning configuration where we are pinning these VMs, we are again getting non-uniform results. Sometimes we are getting much higher throughput, something that we are expecting, but sometimes we are not getting this throughput. So there is some non-uniformity within this NUMA domain. So next thing that comes into mind, there can be other reasons too, but since this was these were isolated cores and we are running these things, it somehow pointed to the topologies. So we went on, we looked at the topology there, and this was the topology. So on the right is the Intel topology, and it is somewhat a typical topology, at least if you're looking at it from the legacy perspective. On the left is the AMD topology where we are seeing the regression. And something that is peculiar about this is there are multiple dies there, and a typical to what happens, what we expect to have, where we expect that there's single L3 domain within a NUMA, within a NUMA node. There are four domains here, basically each domain inside a die, and and all of the cores inside the die share that L3 core. So this is what I was talking about. This is why this is a specific case in chiplet. So even Intel SPR, the Sapphire Rapids is also a chiplet architecture, but how they implement the caches are slightly different. In case of AMD, a set of cores share sort of have their own private LLC, we can say. However, in cases of Intel, even though there are multiple dies, this is not exposed to the software. Basically, there's a hashing function which distributes the accesses uniformly to all the L3s, unless you have enabled the sub-NUMA clustering there. But that is not the case with AMD. Even without sub-NUMA clustering, or NPS, that's what they call it, there is still a non-uniformity there. So yeah, same thing that I told there. But so this is the AMD architecture, by the way. I would be wrong if I say that each die has a separate L3 domain. Rather, in this diagram, we can see that each die has an L3 domain, but AMD has variants where each die can have multiple L3 domains. So Zen 4C, for example, has two L3 domains, and they call it CCX, by the way. Each L3 domain is called CCX in AMD. And between these L3 domains, because these are shared between, these are local to a set of cores, it creates a problem of non-uniform cache access, and the latencies can be quite significant. So the next thing so coming back to a problem, the next thing that came to was obviously, now we have this information. Next thing that came was profiling, and as we said, the inter-cache latencies can be very high, and that's what we observed with this experiment. So basically, if a core in the same L3 domain is accessing gets a hit from its local LLC, it is 4 times faster than getting a hit from a remote LLC. and which is more closer to the DRAM than to the LLC, by the way. And for all this profiling, by the way, we are using per C2C, which internally uses the AMD IBS counters. And we are using this, taking the raw samples and then doing a manual parsing, our own parser. We created our own parser to extract data from it. And these are the sampling rates that we are. So we are sampling every 100,000 cycles. And yeah, these are the overheads. So when the CPU is very active, we get a lot of samples, and this profiling can take up to 6% of CPU utilization on one core. So with this, now that we know all of this, the most obvious thing that comes is, let's put everything together, we'll get the best out of it. And that's what we did. So the second bar, if you can see, we are now getting performance, which is something that we expected in the first slide, right? We then tried with two other configurations, because packing everything within a L3 domain might not always be the best option, because while the number of cores that are there in a L3 domain are limited to single digit numbers like 8 probably, and in the newer generation they are going to be 16, but having the V CPUs can be much larger than that, and that might not be always practical. So we tried with another configuration where we placed the V CPUs together, V CPUs and the V hosts. So in this case, we had a V host net which was interacting. So we placed V CPUs and the V hosts together in a CCX. We got slightly better performance in this case, although not comparable to the best case that we are expecting. And then we tried with another observation, and this was also very interesting observation, was in our case, both the VMs are residing in the same host. So we placed both the V hosts together. The V CPUs are on, they were scattered around in separate CCXs, by the way. So there we observed that although we cannot still reach the best throughput that we can get from it, we are still getting some considerable boost in the throughput, and it was sort of interesting. So it is more scalable than putting everything together. And even in in our profiling also, we found that the V host interaction was the one which was dominating, and that's why we see this result. So these are all observations. So what does this all what motivate to, basically? So it's very obvious that leveraging locality should be something that should be a priority for every application. But here in our case, we're thinking about VMs, and there are some obvious hints that we can get from VMs. Basically, the V host and V CPUs are mostly interacting, and sometimes the V host 2 will be interacting, as we saw. And it becomes important that any VMs which are performance critical, or where there's a lot of sharing happening between the VMs or any other threads, it becomes important that these applications are more cache aware. It also brings more predictability. So with this in mind, we thought of a POC. Why not use the profiling that we are doing and make a solution out of it, some very basic solution, to see if it actually works or not. And that's what we did. So Shivam will be explaining the part of the solution, some challenges that we faced there, and yeah, some what lies ahead in the future. I'll pass it on to Shivam now.
Thank you, Gulshan. Yeah, so the idea of, or the theory of placing the threads which are interacting with one another sounds very good in theory, but what about practice? So let's see how it does in practice. Although it's a generic problem, interacting threads can be any threads, but we basically focused on VM threads here, because that's what our use case was. And we developed a quick POC out of it. So this is a very basic user space scheduler, which does NUCA aware placement of VM threads. And this is how it works. So it starts with finding all the L3 domains on the host. Then it performs its 4 steps in a loop. So first it tries to discover all the VM threads on that host. Then do cache profiling for all those threads. And once we have the data from the profiler, we basically try to identify threads which are interacting with one another. And once we have figured out interacting threads, we try to co-locate interacting threads if possible. Only if this rearrangement is going to give us a benefit. If in some cases it might, the cost of moving threads might be significant, and it might not be a good idea to rearrange the threads. So let's talk about how we actually identify the interacting threads. So our profiler basically gives us raw data where we have where we have the information of which thread is accessing which physical address and how many times. And with that data, we basically construct these two maps. The first one is common. Common IJ is it's a two-dimensional map, by the way. Common IJ basically tells us the number of shared cache accesses between the threads T and TJ. The second one total is a 1D map, and it basically tells us like total K tells us the total number of cache accesses by a thread TK. Now using these two maps, we define the similarity score of a group of threads. How similar or how much interaction there is between a group of threads G. So similarity score of the thread group G is basically this is how we are defining it. 2 times the sum of common cache accesses for each pair of threads in that group divided by sum of total cache accesses for each thread in that group. Now you can imagine that if in a group of threads, the threads are interacting a lot, there will be a lot of shared cache accesses, and the numerator will be higher in that case. So score will be higher. So this is how our similarity score takes care of finding the interacting threads. Now there's one problem with this basic similarity function. So we'll talk about this example and understand what that problem is. So imagine that we have two thread groups G1 and G2, where G1 has two threads T1 and T2, and G2 also has two threads T3 and T4. In case of G1, let's say there's just one interaction between T1 and T2, basically shared cache access. But each of T1 and T2 makes a total of 2 cache accesses. So a score of G1 will be 2 times 1 by 2 plus 2, which is 1 by 2. And for thread group G2, let's say that T3 and T4 have 2 interactions, and each of them basically accesses cache 4 times. So in this case, the score of G2 will be 2 times 2 by 4 plus 4, which is again 1 by 2. So even though in group G2 there is larger number of interactions, still the similarity score is basically the same. So this is the problem with the basic similarity function, that it doesn't account for the volume of cache accesses. And so we basically tried to fix this by adding another log weight to our similarity score, the basic similarity score. So this is how our new similarity function looks like. Now this can fix the above problem. And also the log weight is, the growth rate of log function is basically slower than linear weight. That's why we use log, so that this factor doesn't overshadow the basic similarity between a thread group or among the thread groups. Another thing that I would like to mention here is this factor of 2. We have added this factor because let's say there is a complete overlap between 2 threads. All the cache accesses are basically shared. In that case, the similarity score should be 1 and not half. That's why we have added this extra factor of 2. Now, once we have figured out the interacting threads, or identified the interacting threads, the second problem is how do we co-locate them so that they could share cache. So let's say there are M L3 domains on a system. So now the problem is all about classifying the threads into M thread groups. And imagine that there's an intermediate scenario where each L3 domain has already certain threads running on it. Let's say G1 is running on the first L3 domain and so on. Now new thread T arrives. The question is, where do we place T? Which L3 domain should we choose? And the simple answer here is we'll choose that L3 domain which gives us the highest overall similarity score. So basically we'll choose that L3 domain for which score of GI union T minus score of GI is maximum. So basically this is a similarity score with thread T placed in that particular domain minus the score of that L3 domain without this thread being placed. So this should be maximum for the L3 domain that we are going to choose. This might be negative for all the L3 domains in certain cases where there's no similarity at all for any L3 domain. In that case, we'll choose the one with minimum absolute difference. Now, although this idea of placing the threads based on this similarity score sounds good, but there can be some issues. There are a couple of issues that we have identified. One is CPU pressure imbalance that can result if we end up placing all the CPU intensive threads on the same L3 domain, while the other L3 domain is basically running less CPU intensive threads. In that case, this first L3 domain will face a lot of CPU pressure, and basically all the threads running on this L3 domain will compete for CPU resources and affect one another's performance. While the other L3 domain might not, there'll be suboptimal CPU utilization on that L3 domain. So overall, poor performance plus suboptimal resource utilization, right? Similar problem can happen if we end up placing all the memory intensive threads on the same L3 domain. Again, the same problem will happen here because this particular, there'll be a lot of cache pressure here on this L3 domain. And again, the threads performance of the threads running on this L3 domain will be affected, whereas there'll be suboptimal cache utilization on the other L3 domain because less memory intensive threads are running on that. So because there are two problems, we came up with two constraints to fix them. The first is CPU. To fix the CPU part, we have defined a maximum capacity based on CPU. This is per L3 domain, and this is basically 100% number of number of CPUs in each L3 domain. It was fairly simple to find this maximum capacity, but for cache, we do not know for sure, right? So what we try to do is basically distributing the total cache accesses equally among all L3 domains. So this is what we are doing here. Sum of total cache accesses by each thread divided by the number of L3 domains. But we also allowed for some correction here. So that's why we added this correction factor alpha here. So that in certain cases, we might have to tweak this a bit so that we can find the optimal placement. We can co-locate the interacting threads better. Now, once these constants are defined, we should go ahead and choose an L3. If we are planning to choose an L3 domain for a thread Ti, we should ensure that the capacity, the CPU capacity and the cache capacity both should obey these constants, right? So the capacity after adding, basically CPU uses after adding this thread in that group should be less than the maximum capacity for that overall. So this helps us fix the two problems with the basic similarity function based placement of the threads. Now, as I mentioned in the beginning of the POC work, that it's an iterative process, and I forgot to mention that the frequency is 1 minute. So in every 1 minute, we basically discover the VM threads, do some profiling, and rearrange the threads. Try to rearrange the threads in a better way. This is 1 minute for us, but it's a hyperparameter and can be tuned. Now, the problem with frequent rebalancing is that rebalancing has inherent cost, because when we are moving the threads from one L3 domain to another L3 domain, the cache needs to be, the local cache needs to be moved. I mean, the data in the local cache needs to be moved as well. And this can be significant if the benefit that we are getting in rearranging the threads is not that significant. So basically, to solve this, what we are doing here is that in a given iteration, in n+1th iteration, if the percentage change in the average similarity score is not greater than a threshold lambda, we will not rebalance. So this is how we are trying to avoid useless rebalancing, which can result in overhead. SI here is basically the similarity score averaged across all L3 domains for the ith iteration. Now this is all about the POC. Let's talk about some of the results that we have obtained with this POC. So first we start with the case that we started this talk with, where there is some type of benchmark running on a couple of VMs. So here in this setup we have 6 VMs. VM config is there, running on the host, running on a host, and 2 of them are basically running some non-interactive workloads. So they are basically isolated VMs, right? While VM0, VM2 are running IPF server, and VM1, VM3 are running corresponding IPF client processes. And when we ran our POC work or POC tool, it was basically able to place the VM0's vhost thread with VM1's vhost thread, and VM2's vhost thread with VM3's vhost thread, and other threads were being placed in a way that we maximize the cache resources. And yeah, so we end up placing the vhost threads together. That's what our intention was. And with that, the performance went up by 60%, which was, great. Another thing that I would like to mention is the alpha and lambda hyperparameters that we discussed earlier. So we use actually 20% as alpha, the capacity correction factor, and lambda, which is the rebalancing threshold, is 10%. So if there's the percentage change is not more than 10%, then we are basically skipping the rebalancing. Now we went on to see, okay, now we have fixed the problem of cross VM traffic. How do we, does it work even for intra VM traffic when iPerf server and client both are running on the same VM? So again, we have the same setup, but this time the 4 VMs are running both iPerf server and iPerf client each. So in this case too, you can see, and from our placement numbers, we could easily see that what our tool was doing is basically trying to place VM0's vCPUs together, because there were interactions between the vCPUs of the same VM this time. And hence the performance went up again this time and there was improvement from 10% to 38% in different scenarios. And the numbers here are different because initial placement here matters a lot, and we'll talk about it in a later slide. Then we tried some shared memory IPC workload. We tried this IPC bench micro benchmark to see how shared memory IPC, whether shared memory IPC can benefit from it. And we could clearly see that there's 2x performance gain with NUCA aware pinning that we are doing, right, with our tool. Then we tried a Nutanix specific case where certain user VMs are running and their storage is backed by a CVM, controller VM. Here we have 4 VMs running FIO workload. The other 2 are running storage intensive workloads, non-interactive at all. And we can clearly see that even in this case, there's a performance improvement from 5% to 30% in different cases. Now we also tried a real world benchmark, Redis benchmark. So here we have 2 VMs running on the same host. The configs are there. And we could see that there's 16% improvement in get throughput and 18% improvement in set throughput overall. The results in this setup has a lot of variance because the initial placement here matters a lot. But yeah, at an average, we can see that there's a 16% to 18% improvement in the Redis benchmark throughput. I'll talk about some of the challenges that we face. So one is the inherent cost of software-based profiling, which has its own overhead, and then which also basically is delayed because you pass the data and then you make decisions, and your decisions might not be point in time. If we have improved hardware support for cache access profiling with software context, then we could improve this. We could eliminate the overhead and we could make more point in time scheduling decisions. Also, when we are transitioning from one placement to another, there can be multiple thread migrations and we haven't optimized for that. We should only move the threads which basically minimize the number of thread migrations when we are transitioning. Now, all of our experiment has been focused on a single socket system, and we need to also take into account cross NUMA considerations here. And again, alpha and lambda can vary. So different cases might require different capacity correction factor for optimal performance. So we need to figure out how do we dynamically decide the values for these hyperparameters for optimal performance. Now, there's one interesting case that I would like to talk about. So I basically mentioned this initial placement bias. So let's say there are 2 pairs of threads, T1, T2, and T3, T4. These pairs should behave identically in an ideal world, let's say. Now, if T1 and T2 are placed on the same L3 domain, while T3 and T4 are placed on different L3 domains, this will result into T1 and T2 being able to drive higher throughput because the cache access latency will be pretty low since they are running on the same L3 domain. And so the similarity score for T1 and T2 can be greater than the similarity score of T3 and T4, right? And our placement solver will basically not treat these pairs equally, even though they are supposed to behave identically in an ideal world. So that's one of the issues that we have figured out. There are more, but yeah. That's all from our side. We're looking for feedback and questions. Yeah, it's not downloadable right now, but yeah, we can share it. Yes, yes. Yeah. Yeah, it's a user space implementation. Yeah. Sure.
So in a scenario where you have your VMs running CPU sets that are not CCX,
Okay.
you mentioned on your algorithms that first you find the L3 domains, but it is possible that you are spanning and they're not even fully aligned with these domains. So the profiling part should take care of it, but it's kind of very hard. But how do you choose whether to choose other information that your virtual topology is? Your virtual topology, because you're not seeing this from the VMs.
Yes, yes.
So in that case, would you part the L3 information that you get from the host, the profiling data?
Oh, sorry, I didn't follow. Why do we need to discard?
So your profiling data would give you the actual latency plus threads that are in it.
Yes.
But this doesn't necessarily align with L3 limits because your VMs might be allocated across
Yeah, right. So currently we are not taking into account the latency. We are counting basically the common accesses and taking a ratio. So latency is not what we are considering while placing the threads or basically identifying the threads which are interacting with one another. So what we are doing is, let's say there are two threads. So, and we basically have this map where for each physical address, we know that this thread accesses this physical address this many times. So based on that, we know that, okay, these two threads access the same cache line these many times. So that's our numerator part. And then we divide it with the total cache access for each thread. So latency doesn't come into picture for the, the part where we decide whether two threads are interacting or not. Thank you, everyone.